Hello, I'm Fotios Georgiades, and I will give you an introduction in nonlinear normal modes. Nonlinear normal modes are tools for nonlinear systems. Rosenberg in '60s defined nonlinear normal modes as vibrations in unison of admissible systems, a unified approach for linear and nonlinear systems. Currently, there are two equivalent definitions. The first one is periodic motion, and the second one is invariant manifolds. In this presentation, we will focus on the first definition, which is the periodic motions, and these have been determined numerically with my own codes. Let's start from the beginning. We consider a 2-degree of freedom system, a linear one, and if we perform linear modal analysis by solving the eigenvalue problem, we can have just two frequencies, which are independent on amplitude. Also, the two modes that we get are equal to the number of degrees of freedom. We can plot the responses in time for each mode, and we can have on the left side the response of mass 1 and mass 2 in time, which shows clearly in phase motion, and also that they are periodic. On the right side, we have the responses for the second mode, for mass 1 and mass 2, and it's out of phase motion and also periodic. By adding a cubic nonlinearity spring in the previous system, we have a nonlinear system, and we can perform nonlinear modal analysis by determining the periodic motions of the system. We have, in this slide, we have two examples, and on the left side, we have the responses of mass 1 and mass 2 of in-phase motions of periodic orbit, and on the right side, we have the responses of mass 1 and mass 2 of out-of-phase motions of periodic orbit. These periodic motions are the nonlinear normal modes. By collecting all the periodic motions, we can create plots between amplitude and frequency. On this plot, we have the amplitude of mass 1 with respect to frequency. The cyan lines correspond to the linear modes, and they are just two straight lines, since for each amplitude we have just two frequencies which are the same for all amplitudes. Also, the red line corresponds to the first nonlinear normal mode, and the blue line corresponds to the second nonlinear normal mode. These lines, these curves that correlate amplitude with frequency, are called backbone curves. If we do a close-up of this region, we can have this plot, which corresponds to the first detail of the first nonlinear normal mode, and if we focus in amplitude 0.5, we can see that we have three frequencies on this amplitude. Therefore, the number of nonlinear normal modes can be more than the number of degrees of freedom. By adding viscous damping on the nonlinear system and applying periodic excitation, we can have the frequency response function, which is, for example, taking amplitude of mass 1 over the excitation amplitude when we vary the excitation frequency. It is the blue line on this plot. We can superimpose this plot with the backbone curve, which is the amplitude frequency dependence of mass 1, and we can see clearly that the backbone curve corresponds to the resonance point of FRF. In summary, nonlinear normal modes are periodic motions, and the properties that we showed is frequencies dependent on amplitudes, the number of nonlinear normal modes can be greater or equal to the number of degrees of freedom, and backbone curves correlate with resonance points in FRF. Thank you for your attention.